Hi, everyone, and welcome to a very special edition of Valley of Depth. I'm your host, Mo Islam. Today, we're diving into one of the most ambitious programs in human spaceflight, Artemis, and the technologies that will carry us back to the moon and beyond. Our guest is Kristin Houston, President of Space Propulsion and Power Systems at L3Harris. Kristin's career spans from building some of the world's most advanced rotorcraft at Boeing to now leading the teams designing the engines and propulsion systems that power the Artemis missions. We talk about the state of the program, what SLS is uniquely built to do, the national security stakes of a new lunar race, and how nuclear power and propulsion could redefine exploration in the decade ahead. A special shout out and thank you to L3Harris for powering this episode. On to the show. Kristin, welcome to the show.
Thanks, Mo. Really glad to be here today and looking forward to the discussion.
No, very excited to be here. We have a lot to talk about. We're going to talk about Artemis and all the great things that you guys are doing for Artemis. But before we jump into all of that, let's start with you. You've had a remarkable career across aerospace. I would love to know, how you got to L3Harris, what drew you to the firm, and effectively your kind of career arc. Let's start there.
Sure. I'm actually going to back up a little bit because we're going to see that arc and how it kind of comes full circle. So back when I was in school and trying to decide on what I was going to study, and I knew I was going to do engineering and pick chemical engineering, not knowing exactly what I would want to do with that. But I thought, hey, maybe I could be a doctor. And I realized I did not want to do that very quickly. Or maybe I could go work for NASA. And I never really did anything with that or knew what that really looked like. But I've, kind of meandered since then. And I've had the opportunity to do some amazing things over the years. I spent the bulk of my career at the Boeing company working on military aircraft and specifically rotorcraft and helicopters, and having the opportunity from engineering program management to be able to work on Chinook, Apache, the V-22 tilt rotor Osprey, some marvels of engineering, and really got passionate about the work we do in the defense industry in protecting our warfighters, giving them the equipment they need because they're out, every day with their lives on the line for us and the freedoms that we have here in America, and have gotten very passionate about that. A few years ago, I had the opportunity to come to L3Harris, and it excited me because I wanted to learn more about some of the equipment and the capabilities and the systems that really made those aircraft what they are, and also this knowing that L3Harris has so many different unique systems and capabilities that when we put them together, we can give these unique solutions to customers for their missions. And L3Harris was just 2 years post-merger. I knew we'd be on the kind of front end of becoming that trusted disruptor, and that got me pretty excited. And then about a year and a half ago, I had the opportunity to join the Space Propulsion and Power Systems team, which is part of the legacy Aerojet Rocketdyne, where we're making space engines of all sizes, small, medium, large, and, kind of now coming full circle, that getting to kind of think about, wanting to have been an astronaut at some points when I was a kid to maybe working for NASA someday. I'm working with NASA a lot, and now I get to kind of merge the inspiration and science part of the space exploration with the need for national defense and national security, which kind of comes together in everything that's happening in the space domain today. So it's such an exciting time to be part of space, part of the space race 2.0, and some historic milestones coming up with the Artemis II launch that I know we'll talk more about, but it's been a great joy to have the honor to be part of this role right in this team.
Yeah, no, that's amazing. But since you did mention inspiration and kind of history, and we're about to make history again very soon. Let's talk about the Artemis program. So, Artemis program, it's the Western world's return to the moon, and a question that we get very frequently, unfortunately, very frequently is what I'll say, is, hey, why are we going back to the moon? Right? We have all these issues here. We've already been there. Why are we going back to the moon? I'd love to get your perspective on that one. How do you think about the reason why we're going back to the moon?
Yeah, well, just we'll level set for those listening. Hopefully everybody knows, but the Artemis II mission that's coming up is going to be the first time we've sent humans back to the lunar vicinity in over 50 years. So we have 4 great astronauts, Reed Wiseman and Victor Glover, Christina Koch and Jeremy Hansen, that are going to be the 4 folks that are going to get back there, and then on Artemis III, planning to actually go back and land on the moon again. And we need to do this for so many reasons. So sure, there's an inspiration reason, right? It's this is inspiring to the future generation of scientists and engineers, which benefit all of us by having folks that want to get into STEM careers. And but it's not just about that. There's certainly the exploration and what we can learn. We've learned so much from all of the time we have spent in space. We have a lot of things today that we take for granted, thanks to what has been learned from time in space, whether it's things like GPS or the weather on our phones or microchips. I mean, our cameras in our phones are thanks to that technology that was developed for space. But really, there's a real reason to get to the moon in terms of wanting to live and stay there. This isn't just to put boots on the ground and come back home. We are there to create a thriving lunar economy. We want to learn from that, and then we eventually want to use that to go to Mars and continue that exploration and what we can learn. But we need to do that first on the moon. The moon is a lot closer than Mars. But also, I'd say there's also a national security implication as well. Space is has been the high ground, but is becoming more importantly the new high ground with just where kind of capabilities of our adversaries are. And so we want to be there. We want to be the first to be there. We are part of what's called the Artemis Accords with 56 total countries that have signed on as the Artemis Accords that have agreed that when we get to the moon, where we want to set the norms and behaviors that's going to be expected of us. It's going to be expected that we want to set and we want to have expected for anyone who wants to come and be a part of that those lunar missions and that lunar economy. And unfortunately, we do have adversaries that are not going to have that same desire to have partnership with others. And there are natural resources, there are natural resources that we need to have access to, especially if we want to do propellant manufacturing in the future. There are strategic locations on the moon for some of those national security implications. And there's a real reason that we want to not just get there, that we want to stay there, but we also want to be the first to do it.
Yeah, no, I can't. I couldn't agree with you more. And you've said it more eloquently. I typically just say, well, we're going back because we're staying there this time, and also we have to for national security reasons. So I think no, you hit the nail on the head.
That's a great summary, and
yeah,
key points. Yep.
And it brings there's parallels to Apollo for and a lot of obvious kind of parallels when you kind of look at it from top down. Apollo was really important in having the first boots on the ground was really important for a lot of scientific reasons and exploration reasons. But at the time, there was also an adversary that we had that we were in a technological arms race on, trying to see who was going to get to the moon first. And you're starting to see signs of that today with a new adversary. So completely agree. The importance couldn't be greater. And I think it's, I could argue that the political coordination around it could be better, but that's for us to cover. That's for us to cover another day. Let's talk about the state of the Artemis program today. So there has been a first mission, Artemis I. What is the current state of the program? How are things looking?
Well, first I'll just highlight that Artemis I was a huge success on the very first launch of a newly developed rocket. It had 99.9764% accuracy for the orbital insertion. I mean, that you don't get much more precise than that. And on its first time, right? So
Yep.
We know that this rocket is proven. We know Artemis II and future Artemis launches are going to be just as successful. So we did prove it out on Artemis I. And now, as we get ready for Artemis II early next year, things are coming together really well. Down at the VAB, down at Kennedy Space Center, it's all coming together. We're essentially putting on finishing touches at this point. We're getting ready for a rollout, and it's coming together really well. So I think we're gonna obviously stay diligent on every single step that we have to do to get to the launch day. But we are on a really good trajectory to get that launched early next year.
Well, tell us a little bit about L3Harris's involvement in Artemis. What is the technology that the company is responsible for?
Sure. We have components across that entire rocket. So we have 89 different elements on Artemis II and Artemis III. When we get to Artemis IV and beyond, we actually go up to 101 elements as we move to the exploration upper stage. But we have propulsion. You see those big engines at the bottom, those RS-25s engines. They have a heritage through the space shuttle main engine. They put out 500,000 pounds of thrust apiece. So it's over 2 million pounds of thrust. So it really, those astronauts, they're going to feel it when those engines light. We have the RL-10 upper stage engines on the ICPS upper stage. On the Orion spacecraft, we have multiple engines and propulsion elements. We also provide the audio system on Orion. We have avionics throughout the boosters, the core stage and the upper stage that help operate those elements as well. So we really have components throughout the rocket. So we're really proud to be supporting the Artemis program and looking forward to this SLS launch for Artemis II.
Well, let's talk a little bit more about Artemis II. Like what I mean, and you alluded to it. We're going to bring humans back to the vicinity of the lunar surface and the moon. But what is the purpose of Artemis II? Like what needs and maybe you can also shed a little bit of light of like around Artemis I. Like what did we hope to achieve for the mission? And it sounds like we achieved most, if not all, of our goals for sort of the technical kind of readiness of the vehicle and all of its components. But for Artemis II, also, like, what is the goal of Artemis II? What does success look like?
Yeah, so like you said, so for Artemis I, as you said it, that technology readiness, we proved it out. So first, we are always thinking about when we talk about human spaceflight. We are very much remembering that everything we do is going to impact those 4 astronauts and their family, and we want to make sure they get home safely, right? So it's very, very much in the forefront of our minds that we have to have a quality in our work, and that has to work as expected. So you do an Artemis I to prove out all the systems, make sure everything's going to work before we put crew on board, and like you said, completely successful mission. For Artemis II, now we have crew on board. They are going to go and circumvent the moon, going further than humans have ever gone, and again back to that lunar vicinity for the first time in over 50 years. So we really want to prove out again that everything is working as expected. They're going to do some proximity operations with the upper stage to show that Orion can be manually maneuverable, so that eventually when it's going to need to dock to a gateway, it's going to have the ability to do that. So we're expecting, that's going to be part of the demonstration there, and they'll continue to do other checkouts and to see what they learn from their time being up on mission.
Yeah, well, there's during the Apollo missions, they had one particular mission. I forget which one. I should know this, but which number it was. But the Eagle, descended, like basically did sort of a maneuver as if it was landing on the moon, but it didn't. It came back into orbit. Will there be something like that? I know you're kind of alluding to there are going to be some type of orbital maneuvers, but how closely are they going to try and kind of mimic that kind of ultimate trajectory of landing?
Right. So they're not. This mission is not for landing. The Orion spacecraft won't be the lander. There are human landing systems being developed by SpaceX and by Blue Origin. So this is not as much about landing, but is about getting Orion spacecraft being able to be piloted to go around the moon in a trajectory that it can take for the future as well. But there will be some proximity operations again, where the Orion spacecraft will be able to undock and then do some flying and then redock with that upper stage. And again, in future missions, when we have the Gateway, which is going to be a small kind of space station that'll orbit the moon, that for astronauts to can stay in, potentially as they then transfer down to a landing, wouldn't be able to show that proximity operation works well. So there'll be some tests for that. But in terms of a landing, won't actually be landing on this one. But we'll be getting, again, what we learn so that we are ready for landing on Artemis III. And, we always want to take incremental steps, make sure we're managing the risk and we're being smart about, any risk that's being taken. So we're, as a test program, you want to continue to just do more and more each time. So we'll do a lot of the great operations, but won't do prep us for landing in the future.
Right. So you mentioned this earlier. Artemis I was impressively accurate. I didn't know that number, but yes, impressively accurate. It's amazing for a vehicle. It kind of just shows, look, ultimately, I know there's a lot of back and forth about, all right, well, what methodology works best? Should you, engineer the product, make sure it works, then launch versus test and fail. So to get that right first time so accurately, I mean, that is just purely very impressive. What lessons from that mission give you sort of like the most confidence going into Artemis II that you're like, hey, look, these things we've proven out, like we feel really, really good that Artemis II is going to go just as well?
Yeah, well, we're flying same configuration, and that rocket, like you said, it performed flawlessly. So that gives us that confidence. We have, great teams that are working on it. Again, we know we care a lot about those 4 astronauts that are going to be on that rocket. So we've put that same level of diligence and quality and detail into every single thing we've done to make sure that rocket is going to be performing just as well as Artemis I. So I have full confidence in it.
All right, so Kristin, tell us where's Artemis II right now in terms of readiness, risk, and pacing? Like, I know you mentioned early next year is what we're targeting, but where do things stand today?
Yeah, we are making really great progress on Artemis II down at the VAB at Cape Canaveral. Things are coming together. The stacking is in process. Orion is ready. It'll be stacked here shortly. And then we'll have the rollout early next year. So we are very ready. It's really kind of the last things coming together over the next several months. But we are making really, really great progress, and we're ready. And I know Artemis II is going to perform, like we said, it's going to perform just as well as Artemis I, and we're going to be ready here. So a couple big steps coming as we get that rollout, and that'll be exciting when we see, come out and get rolled out of the VAB, and then we know we're going to be really, really close.
Yeah. And then my last question on Artemis II specifically is like, what does it look like from L3's perspective on like what needs to go right from the propulsion and avionics vantage point? So like from, I know, you mentioned the engines, of course, to start, but maybe walk us through a little bit of that sort of life cycle of what exactly is going to be involved throughout sort of kind of leaving Earth to orbiting the moon.
Yeah, so it starts actually as part of the countdown, right? We actually light our RS-25 engines 6 seconds before liftoff. So in that countdown at T-6, our engines light. Those are the 4 main engines there, and that gives us in those 6 seconds to make sure everything is checking out right. I mean, we do lots of checks leading up to that day and that moment, of course, but those 6 seconds, because you can stop and abort a liquid propulsion engine like the RS-25 if you needed to. Because at T0 and it's liftoff time, those solid rocket boosters light, and when those light, you're going. So we have that ability in those couple seconds to make sure everything's working. So when the solids light, and they will separate about 2 minutes after takeoff, and they stay lit for 8 minutes. That's a really long time for an engine to go. So for 8 minutes, those rockets will be given again that 2 million pounds of thrust, and then until we get to the separation of the upper stage engine. So, and then at the upper stage, we're going to be watching that our RL10 is lighting as needed and burning as needed. We'll be watching that. The Orion spacecraft, as especially when they do that undocking operation, making sure those propulsion elements are working as well. So we, throughout the entire mission, will be making sure our propulsion is working as expected. Again, it's on the launch too, the avionics components on the boosters, on the main stage, on the core stage, on the upper stage, will be helping guide those components those elements as well. So, we'll be instrumental throughout, and we'll have our teams there working to make sure everything is going exactly as expected.
Okay, so I want to zoom out for a second. Let's talk about SLS, the vehicle itself. Tell us a little bit about what is unique about SLS technically and programmatically.
Sure. So SLS is the only rocket that can take us direct to the moon. It's the only one exists that can do that. And like I mentioned, it's proven we can do that. It has high thrust and can carry a lot of payload, so high payload capability. And it's really optimized for that high energy orbit. There's a lot of talk about reusability and thoughts of the need for reusability. And there are certain missions that it really does benefit to have reusable rockets, but reusability it can be anywhere from a 25 to 33% performance penalty, because you need to carry enough fuel to then have that fuel and propellant to get you back, to get the elements back. So, given that we are going direct to the moon, we are optimized for that with the SLS rocket, and it's the only one that can do it.
So, that's great, and obviously it's been a huge improvement from previous launch vehicles. But I do want to talk a little bit about the criticism around SLS. particularly around the cost, the cadence, the complexity of the vehicle. From your perspective, what do you think is fair? What is more outdated? Like maybe it was a fair criticism before, it's not anymore. And then what are some of the things that have been fixed about it? Would love your perspective on that.
Sure. I mean, the thing to think about now is we really are coming from the development phase down, and now we're really transitioning to more of a production phase. And development is where you're learning a lot. You're making changes as you need to, and you're working through everything for the first time, right? So there is typically a higher cost during a development phase. So now that we're moving into more of a production cadence, I mean, Artemis II is at the VAB, the core stage for 3 is right behind it. There's work. I mean, we're working on engines up through Artemis IX right now on our RS-25. So we are coming down those learning curves, and the cost is coming down. And we are going to see costs coming down as we get into a more regular cadence. So we do need continuity of funds and clear that we're going to continue those missions. So we keep driving down those curves. There's been a lot of cost that has come out too. For instance, on our RS-25 engines, again, they have a legacy from Space Shuttle main engine. We've already taken 30% of the cost out from the Space Shuttle days, and we're on a path to have them be 50% lower cost than they were then. And so there's a lot of effort that's driving out that cost. I think you're going to see the cadence will continue to improve and accelerate as now that we're moving again more of a production mode and have gone through a lot of the challenges of development. So, the other thing is we're working on multiple rockets at once. There's multiple rocket configurations. There's the Block 1, the Block 1B, the Block 2. So we're really working on different configurations that continue to build on payload ability and continue to increase the capability of the rocket. And those are happening all at the same time. So I think there's a lot of nuances when it comes to, what is the cost and what are we doing that you need to kind of understand some of the details on. So I think sometimes the criticism just looks at the very top level and doesn't understand some of those details. But I think we've made really great progress as an Artemis program and on the SLS rocket. And I think we're going to continue to see that improve again as we get into a more steady state.
All right. Well, let's also then talk about another very large rocket that's being developed right now, Starship. So, Starship's had a kind of initially a really great test campaign, and things have started to get a little bit more. It's been harder for the business recently, and I think now with the latest test, things are looking like it's back on track. But I do want to ask sort of the big question here, which is like, how does Starship play into the calculus of Artemis? And do you see a world where both technologies, the SLS and Starship, coexist?
Yeah, they have very different mission objectives, right? So the SLS, again, is designed to go direct to the moon, direct to those high energy orbits. And when we do that direct insertion there, and we can take astronauts in Orion directly to that lunar surface, we are not having, the refueling missions or the complexity that can potentially put astronauts at risk by having kind of that more complexity of architecture and mission. So there is a purpose for SLS to go direct, but Starship has a purpose. Starship is optimized for heavy payloads to LEO. And, so again, they're just very different purposes. So they really probably shouldn't be compared because they do have different purposes. But Starship, it's a critical element of the Artemis architecture. So when we are going to land astronauts on the moon, Starship is the human landing system, is one of the 2 human landing systems being developed. Blue's also developing one. So that Starship, it's going to go to LEO. It's going to need to be refueled to be able then to get this landing system up to dock with Orion, and then eventually take astronauts to the lunar surface and to go back up to get them to come home in Orion. So I think there is a role and a need for both SLS and for Starship. There are different roles, but Starship is critical to Artemis's success. It's going to be critical for Artemis III when we do want to land humans back on the moon. But they do have different purposes as a rocket themselves.
Got it. Okay, that makes sense. So I want to jump back to the kind of nature of the Artemis program. We talked about sort of the importance of the Artemis program for exploration, for science, for inspiration. Let's spend a little bit of time on the national security piece, which you and I both alluded to. What is the sort of national security sort of return on investment from having sustained lunar operations? So like comms, cislunar awareness, logistics, having a base there one day. What is the importance from a national security perspective?
Yeah, well, you just mentioned a lot of them. Space is the high ground, and we need to have that presence there. You know, China is making really good progress in their lunar program. They are expecting to land astronauts back by 2030. They're talking about crewed missions in the 2030s. And they have been making really, really steady progress to that goal and being very successful on that. So we are in a space race 2.0, space race of today. And if they get there first, they are not going to be as willing to be open to international partnerships and sharing of resources and learning together. We've seen that. I mentioned the Artemis Accords. They are not part of it. We can look at what we see from operations in the South China Sea today, and we can expect that kind of behavior back on the moon as well. And I think Congressman Brian Babin has had a great quote that he said a number of times that I have echoed, continue to echo. And he said, just imagine this. We get to the moon and we land to find a sign that says no trespassing in Mandarin. And we do not want to face that, right? So that's a real reason that we need to be the first to get there. And again, there are national security implications. We want to have a lunar base. There are natural resources that we want to use for mining, for future, for propulsion, for propellant, for use there. And if we can get there first, it's with our international partners, the 55 other countries as part of the Artemis Accords with us, the 56, we'll set the norms and behaviors of how we're going to operate there. And once we get there, we will, again, have a thriving lunar economy. But the need to be able to have that high ground, the ultimate high ground in space and with the moon is going to be critical for all the national security implications in the future.
Do you think we're underestimating China's ability to land on the moon? Like, do you think that they, forget about who comes first? Like, do you think that they ultimately, let's just say 15 years, the next 15 years, will they have landed on the moon?
I think they will. I think it'll take them less. I think they've made really good progress, and they are continuing to kind of click through different milestones on that progress. They get determined on what they want to do, and they will put the effort in, and they'll get behind it. They will fund it. It's a national imperative for them, and they will get there. I don't doubt that they'll be able to get there.
And I would love your perspective on, I talk about the show quite frequently, but For All Mankind, first episode, Soviets land on the moon first. It's sort of this dystopian, backwards looking sort of take on what would have happened. What do you think the societal impact would be if now I know we've got there first. We already have that, but we haven't been back in a very long time. I think since 1972. What would you think the societal impact would be if we let China land on the moon back before we get back?
Yeah.
Or land first before we get back.
It is interesting. So I love For All Mankind. I finished that not long ago, and it was a really great show. And to think about the what ifs, and it does make you think about the what ifs of today, right? It feels very relevant to there could be this alternate history of what if, who gets where first, and what could happen to the other if not. I think if I would be really just disappointed if we kind of, from the U.S. perspective, give up on that vision and that kind of dream to go be able to do this. And it is about living and staying on the moon. But again, eventually to get to Mars and further exploration, we need to learn from that. So I think if China gets there first and really kind of starts thriving there, I think I don't want us to be in this constant catch up mode, right? So are we going to be chasing, or are we just does that mean we just give up because China's already there? But then what does that mean for future exploration, for future needs, again, for national security? There are strategic locations on the moon that we want to get to first, right? So some parts of the South Pole of the moon, that we want to be there. So, I mean, obviously the moon's a big place, so sure, there could be room for everyone, but, I think of it as kind of like here on Earth, there are places you want to be and places you don't want to be. You don't really want to have to go settle in the middle of the Saharan desert. You would much rather be in the fertile grounds of the Midwest U.S. And so we want to make sure we can get there. And again, it's not just for U.S., but for the whole international community that is partnered with us and looking for that continued leadership in space.
Yeah, and I know we also have a additional perspective, which is like, when you think about the Apollo era and you think about the fact that we were in a Cold War at the time, how impactful it was from sort of like the global leadership perspective of for the U.S. landing on the moon, and we were at that point, technologically like slightly behind, right? Sputnik was first in terms of the first satellite in space. Then, we didn't send the first person to space. It was Yuri Gagarin, which was again the Soviets. So we were like kind of constantly in this like behind. And then we made this leapfrog and made it to the moon. And I think we kind of reset things like globally, where it's like, okay, well, the U.S. is superior. The U.S. is technologically superior. Democracy does work. And I think that's sort of like the sort of more existential question, I think, which is like, if China lands for the first time before we return, what does it say about sort of the different kind of methods of democracy versus communism and socialism? So anyway, those are whole other questions which we can talk about. But I do think it's critically a lot of implications and critically important. I want to switch gears here and talk a little bit about sort of energy on the moon, because we send, there's been private companies that have landed on the moon successfully so far, but, there's always this issue of like surviving the lunar night and how much power do you have? And a lot of these landers don't typically last for more than a week or two, right? So like, tell us a little bit about like, what does the energy landscape look like for us on the moon? And also tell us a little bit about L3Harris's history with kind of energy technology in space, because I know there's quite a bit of history there.
We do have a long history there. So I'll just first start. I mean, like you're saying, everything needs power, right? So, I mean, I don't know about you, but every night I'm plugging in multiple devices and I'm, we're constantly looking for power cords and how are we going to charge this device or that device? Or, now some folks with, might need it for your car to get your transportation, and power is so key in everything we do. And I think we're always constantly thinking about power. Well, just like it's here on Earth, it's going to be the same up on the moon. Everything needs power. So like you said, the rovers, the habitats that we'll have, anything we want to do, it's going to need power. And like you said, keeping warm. So surviving the lunar night, it gets down to minus 280 degrees Fahrenheit, right? And the lunar night is 14 Earth days. That's all 2 weeks of really cold, no access to sun. So a lot of what we have today in space is solar powered. That's not going to be an option if we want to have that long-term sustainability. And then on the plus side, it does get really warm too. It gets up to like 260 degrees Fahrenheit. So you're going to want some cooling systems as well. So to be able to survive, we're going to need power. And one of the things we're looking at to be able to generate enough power is the program Fission Surface Power. So it's a fission reactor, nuclear reactor that can generate a lot of power. We have been working on a solution that's a 40 kilowatt solution. They recently came out with NASA and Acting Administrator Duffy wanting to go to a 100 kilowatt solution, which is great because like we said, there's going to need to be a lot of power. So we're scaling our design up and had a scalable solution. So and want to launch here in the next few years. And it's very doable. You mentioned our history with L3Harris. 60 years ago, we launched the only nuclear reactor ever to launch into space. It's a SNAP 10A. It worked well. There were some other components that failed that didn't get it as long a life as it was expecting to, but the nuclear reactor part of it worked as expected. We did it 60 years ago. So I keep saying, well, we did it then. We can do it again. We can do it now. And we did that from start to launch in 5 years. So it is doable. We've made great progress. We're partnered with Westinghouse for the reactor piece of it. We work the power conversion and the power management, the power distribution that's going to be needed. But to put in perspective, the 40 kilowatts, that's enough to power 30 households for 10 years. So it's a lot of power. So then we can scale that up to the 100 kilowatts, but it's a lot of power. But again, we're going to be powering rovers and habitats, human life systems for astronauts that are there on the moon. We want to, if in the future, if we're going to be wanting to generate propellant, we're going to need megawatts, right? So we have to start with something. So I think the 100 kilowatts that we're moving towards now is a good solution. It's large. It'll be able to be building blocks for that future. And it's all going to require power. So really excited about the history that L3Harris has had and our legacy. Building on that, we've continued that development and building on that, and now seeing a real push and recognition that the power requirements are needed, they're real, and look to be being accelerated.
What's the minimum level of like power that we can sort of get away with on the moon for the time being? Like, I know you mentioned 40 kilowatts. Is that the number, or is it more like 100?
I don't know that it's a specific number for right now. It depends what's all going to be out there. We use nuclear power with our multi-mission radioisotopic thermoelectric generators. Those essentially, I think of those as just little nuclear batteries. They're powering the Mars rovers today. So L3Harris has produced those for many years. They're powering those, or it's going to power the future Dragonfly mission to Titan. And so things can have some power within them. So it's hard to say specific because of what's all happening, what's there, the needed. But I think the 100 kilowatts is a good amount of power that we're going to start building that foundation with.
Why is the administration now accelerating all of this, especially around nuclear, right? There's a kind of renewed focus on nuclear. So like from your vantage point, what's changed?
Yeah. Well, first, I'm really excited to see the focus on it. The Fission Surface Power program started several years ago with some of the early concept designs and development. But now it's really, like you're saying, it's really getting traction. I think there is a recognition that China is moving out and we need to, accelerate this. And I think also just the realization that we have all these, visions and plans for this lunar habitats and rovers in this lunar kind of economy and there. And we can't do it without power. And like you said, survive the lunar night. I think it's just all kind of the recognition that that's needed. And I think seeing that we are serious about wanting to create that presence on the moon, and that power is going to be needed to get there. So I'm thrilled to see that there has been kind of a resurgence of support and an acceleration on the timelines, because it is going to take a couple years, but it's very doable. Like I said, we've done it before, and we're ready, and we can do it again in the next few years.
So let's talk for a second on nuclear propulsion. So nuclear propulsion in general gets a lot of, there's a lot of headlines out there, and it's see them all the sci-fi movies, fission powered propulsion, fusion powered propulsion. What's hype versus just like hard physics right now? Like how far away are we from like an actual system that is powered on nuclear propulsion?
Yeah, I mean, we're within, if there is a real desire to go do it and the funding to back that, we're within a few years, we can have a nuclear propulsion system. The technology exists. Now it's using fission power. I think if we want to talk about fusion, that's a little further off and more challenges when it comes to that. But we look at, for us, we say, hey, we can have like a nuclear electric propulsion system here very, very near term. So the work we're doing on our Fission Surface Power program, so taking kind of that reactor and that system, we see we could couple that with our advanced electric propulsion system. That's a 12 kilowatt Hall thruster that is going to be used on the Lunar Gateway. So that's the gateway is the space station that'll orbit the moon to dock with Orion and the lander. Gateway will have 3 of our AEPS systems with these 12 kilowatt Hall thrusters. So we could take that AEPS system with our FSP solution and essentially put those together to have a nuclear electric propulsion system. And from a nuclear thermal perspective, propulsion's perspective, that technology, again, we have some of the nuclear reactor technology has continued to be developed. The nuclear thermal propulsion is a little bit more of a traditional kind of rocket engine. So I think it's all can be there within the next couple of years. And we really need both. We're talking a lot about, missions to deep space and to Mars. And to be able to get there in a more timely way, we can use nuclear electric propulsion. It's so much more efficient in a nuclear electric to be able to take those long duration missions to Mars, like moving cargo. But as we're talking eventually about wanting to move humans, we're probably going to want a nuclear thermal propulsion system because we're going to be able to do that much faster. We're going to have that long-term energy that a chemical solution can't provide, but then also be able to minimize the time, of exposure for astronauts to radiation and things. So I think it's all doable in the next couple of years, as long as we have some constancy of purpose and leadership in wanting to go do that.
Yeah. Well, it's exciting, and it would be, obviously it'd be a game changer for a lot of reasons. But one thing that kind of came to mind, and I'm going to go on a slight tangent here, Kristin, based on, our conversations about propulsion and effectively maneuverability in space, and of course the national security angle. What do you think about, space is the ultimate high ground. We've been talking about that in a lot of different ways today. Like, what how important is maneuverability in that sort of framework? And also feel free to throw in like, hey, maybe in the future, like this is where nuclear propulsion will come into play. But just curious, like sort of this maneuverability advantage in space, how important is that? And how are you guys thinking about sort of your systems in that context?
Yeah, I mean, maneuverability is the key in the future. So the space domain now has gotten more congested. So there's a lot more assets in space. It's also contested. So our adversaries are out there, and we need to be prepared to be able to quickly maneuver to whether it's an offensive or defensive maneuver, right? We're going to have maneuverability. And traditionally, I think of it, I kind of have an analogy that I like to use. So traditionally, we've been, most of the propulsion there is just kind of just station keeping on orbit. So I think of it as these small little thrusts, kind of like lane keeping assist, right? You get a little nudge back to keeping your lane and just these little nudges, but you just want to keep straight in your lane. So we're going to keep on orbit as we've been going. But in the future, again, given it's going to be a lot more contested situations, we might need to not just stay in our lane, but let's say cross 5 lanes of traffic whizzing by you very quickly because you just realized your exit's in the next eighth of a mile and you got to quick get out of the way. So we need to think about chaotic orbits. We need to think about, again, quick moves. So we're going to need that high thrust, high delta V to be able to have that maneuverability. Again, whether it's offensively or defensively. So I think we're going to see that become much more critical. And then also our adversaries have good insight. When you're just staying straight in your orbit, you're very predictable, right? So we need to become unpredictable as we go forward. So I think there's going to be a lot of need for that. We even have solutions like our RL10 that can have multiple relights. So, it can go sit in space. It can then relight and move and reposition when it needs to after having been stationary for some period of time. But I think, you hear the Space Force talk a lot about maneuvering without regret or dynamic space operations, right? So it's propulsion is going to be that key element to help us be successful with all of our space-based assets.
So, I know you mentioned the various propulsion systems that you guys are going to have on Gateway and the like. Are there any of those systems that are feeding towards any defense missions?
Yeah, so today we do have chemical and electric propulsion that serve defense applications. We're on some of the missile warning and missile tracking satellites. We are on other defense, based applications as well. A lot of those we can't really talk about what they all are, but we today do play a role with our chemical and electric propulsion in a lot of those missions today.
Well, I won't pry any further then. We can. Okay. Well, look, you brought up you brought up missile tracking, so we got to talk about Golden Dome.
Of course.
So what? So tell us a little bit about. Tell us. Are you guys doing work within the Golden Dome architecture? I'm assuming you are.
Yes.
And yeah. And then what do you think the Golden Dome looks like in practice? And tell us a little bit about how propulsion and power fits into making it real. We can do a whole podcast on just the Golden Dome, so we don't need to get into all the intricacies. But just at a high level, would love to touch on it.
Absolutely. So L3Harris is really poised and well positioned to support Golden Dome. We have a lot of existing technologies that are already proven out that it can be key elements that are ready today. Some of them are operational today. We have production lines that are up and running. We are ready to scale. In a lot of instances, we have already increased capacity to be able to do scale and acceleration of assets that are in production today. That'll be key elements from both the propulsion side, but also some of the satellite pieces and various elements that L3Harris provides from a broad L3Harris perspective. And so we think we really can be very supportive and critical player providing that. And really wanting to do this more quickly, we need to leverage that high readiness technology that's out there, again, with those hot production lines that's already been proven out. Now, from a more specific space, the propulsion element or the power element of it, I think what we were just talking about with being able to have that increased maneuverability, what we're seeing is we can really leverage our existing technology. We are scaled already. We've already invested and scaled from our thruster perspective to be able to deliver more. assets for the needs. But we really see we could take our chemical propulsion because we have monoprop and biprop propulsion systems. So, again, high thrust, high delta V solutions with some of the electric propulsion that can help for kind of longer endurance of missions. Have hybrid solutions, hybrid propulsion solutions, or ability to have multi-mode propulsion solutions that can you can sit out there and stay for a long time. And then when you need to, very quickly move with a monoprop or biprop chemical solution. We have our RL-10 that has the ability to relight. So again, we could have we could launch something and after quite some time of being kind of dormant, then relight again and reposition or release other assets as needed. And we're also working on things like more advanced propellants that give us 25% more fuel efficiency, so we can get more out of the assets that are in space without having to do a major redesign. But we can just get more efficiency, more specific impulse from that. So a lot of different things in work in terms of kind of our really high readiness level solutions that I think are going to be critical to Golden Dome.
So just as we close here, I want to talk. So you have a pretty extensive propulsion portfolio. That's very clear. What areas of that portfolio do you feel like you're kind of pushing the hardest? I'd be curious to know, meaning pushing sort of the boundaries and the sort of the edges of innovation, so to speak. And then looking out, call it 10 years from now, what's a propulsion milestone that would make you the proudest? And what would that enable that we can't do today?
Okay.
I have a guess of what you're going to say, but I'm very curious what you're going to say.
Okay. I'm curious what your guess is. What I'm going to say. Let me take this in two pieces, right? So first,
sure.
The first piece, kind of the innovation technology. We are innovating all the time. I mean, we have 60 plus years of heritage of, proven on orbit solutions with our propulsion. We're back from the very beginning of the Apollo era, right? So we have a lot that we've learned from, but we have continued to innovate. So we are doing things, whether it's looking at VLEO propulsion solutions. That's a challenging environment for propulsion, for elements, and it's going to be a really key area, again, part of Golden Dome. So we're doing a lot of work kind of in the VLEO area, talk about some of what we're doing on a different propellant, continue just regular innovation, but we're also innovating a lot in terms of different manufacturing techniques and technology. We do a lot with additive manufacturing that has given us the ability to do a lot more faster, cheaper, definitely faster, and faster is going to be what we really need to. But we are, and we're not just doing kind of a lot of folks say, we're doing additive manufacturing. We are, but we're really doing additive with these exotic alloys that are able to withstand temperatures of up to 6,000 degrees. Because they see really harsh, a lot of these components see really harsh environments going from launch and then into space, extreme highs, extreme colds of temperature. And so we've really done a lot of work from an additive perspective as well. So a lot of great innovation, whether it's on the manufacturing material side to just different actually technology solutions. And then, we've talked about the nuclear side as well. I think we've done a lot from the nuclear power and nuclear propulsion perspective. So then, 10 years from now, what would I love to see? I mean, first, I'd love to see a thriving lunar economy, and propulsion and power are keys to all of that. I would really love to see that we have launched an FSP solution, and I'd really love to see that we are starting to use nuclear propulsion as well. And I think we don't have to be scared of it. We have, there's a lot of fail safes in place. These reactors, they launch cold. Again, we have done it before, so we know what to do, and I think it's really needed. So I'm really excited for that because I think it's going to help not just the lunar economy, but as we talk about wanting to go to Mars, and we've talked, a lot about both of those. But I also would like to put it in perspective. The International Space Station is actually kind of close to Earth in the grand scheme of it. It's 260 some miles above Earth, right? The moon is 240,000 miles from Earth. So, International Space Station, you can come back in a day, in a couple hours if you needed to. You could get back to the moon in a couple days if you needed to. And then you get to Mars, it's 140 million miles away. That's 9+ months of a trip to get back if you need to, right? And so just putting that perspective and just I want to see us be able to continue to explore, continue to learn, continue to protect our homeland and keep the high ground from that national security perspective. And then also, all of this also, just like we talked about at the very beginning, inspires the next generation. And, all those kids who are going to grow up to continue to evolve everything we are doing from a science and engineering and technology perspective. So I think a lot of good to come in the next 10 years, and I'm looking forward to seeing our progress.
Well, no, that's very well said, and I share your optimism for the future. I know sometimes it can be hard, given the state of the world, but this is a exploration and science and the engineering that's getting the edges of engineering and the boundaries of engineering that are getting pushed every day is very exciting to see. So, Kristin, it was great to have you on the show. Thanks so much for being with us.
Thanks for having me.
Really appreciate your perspective, and it was great to kind of dig in. And we haven't had L3Harris on the show before, so this is great to get you guys on and talk about all this. So thanks so much, and until next time.
Yes, thanks, Mo. Take care.